Where are you guys coming from?
Columbia. Cool. What's your response?
There's bathrooms down there.
Do you hear me? On Zoom. Can someone confirm it?
Three people on this.
Yes, 8 people.
Maybe 5 minutes.
Yeah, sure.
Some people on the Zoom. Do they care if I just talk here?
What?
The people on the Zoom here.
I guess I'll read that.
Like they know we're waiting 5 minutes.
Yes.
We're just waiting a couple minutes.
Okay, we will start in 4 minutes.
as we wait, I'm Shai. We're waiting a few minutes for more people to arrive. So I saw that some people from Columbia came. Where's you guys were NYU?
Yes, with our own.
Oh, I was just wondering where people came from, because people come from different universities.
Okay, fine.
So, just waiting to see if people, because I think there's some people coming from maybe City College and the Flatiron Institute.
These are like Wi-Fi slips for anyone external who's having a hard time signing up to Wi-Fi.
Yeah, we're waiting a couple minutes. See if more people from other places are coming. Do you guys know if other people from Columbia are coming? I guess we're not. Somebody emailed me from Columbia this morning, or by this morning I mean 40 minutes ago. On key. Maybe we'll start with that. On key mute. And Q on. All right, Himanshu has arrived. Now we can start. All right. So thanks for asking me to give these lectures. This is going to be a series of 6 lectures on formal field theory, starting from, I guess, knowledge of basically nothing, and then concluding with practical demonstration of how to solve, for instance, the 3D Ising model, as well as other conformal field theories. So I mentioned the class is going to meet twice a week, Mondays and Wednesdays, and there's going to be assignments after each class, which I will email everybody about. And so I encourage you to do the assignments if you really want to know the nitty gritty. But of course, if you also just want to follow along, that's cool too. And so, encourage you to attend regardless. Okay, so what are CFTs? So CFTs are just quantum field theories with conformal symmetry. So I should note that you actually don't even really need to know what a quantum field theory is for this class, because everything relevant to quantum field theory we will actually discuss. So although you should know a little bit about quantum mechanics, I do. So what is conformal symmetry? Conformal symmetry is the spacetime symmetry group with 4 elements. So one is translations. This is where you have some spacetime point x and you just shift it, x plus a. Secondly, you have sorry?
No, probably it would be better to have lights on the board, right?
Okay. Then you also have rotations, which is where you rotate a spacetime point with some matrix n.
Yes.
And so these 2 elements, translations and rotations, this is what encompasses what's usually called the Poincare group. And so the Poincare group is usually the spacetime symmetry group, which is how we define relativistic quantum field theory. So that's kind of just like standard relativistic quantum field theory for these 2 guys. The novelty of conformal symmetry is 2 extra elements. So you also have something called scaling symmetry, which is where, this is the matrix. Scaling symmetry is where you literally just multiply all the spacetime points by some overall factor, let's say a. So you can rescale everything. And this is really kind of the defining feature of conformal field theory. This is where a lot of the power of conformal field theory is going to come from. Although there is in fact yet a 4th element of the conformal group, which is basically a fancier version of inversion symmetry. So just for simplicity, I'll just call it inversion, although I guess in roughly 45 minutes I'll give a more precise definition. But this less precise definition is that you basically invert a spacetime point to the original point divided by its magnitude squared. So roughly speaking, these are the things that encompass conformal symmetry. And so if you just have a quantum field theory with conformal symmetry, i.e. these additional 2 symmetry elements, scaling and inversion, that is a conformal field. Now, why do we care about conformal field theory? This would seem like a pretty random couple things to add, scaling and inversion, like how many systems in the world actually have these extra properties on top of just the usual translation and rotation. And so it turns out that conformal field theory is actually ubiquitous and in some sense kind of part of the definition of what quantum field theory itself is. And so the reason is that one way of defining what quantum field theory is that we start with some description of the theory in the UV, which is at very small distances or alternatively very high energy. And then we flow, which can also be understood as zooming out, to the IR, which is very long distances, alternatively low energy. And this is basically the definition of quantum field theory according to the modern understanding of quantum field theory introduced by Ken Wilson and many other people. And so like to give an example, like something like quantum field theory in UV, I mean, UV could be almost anything. It could be like a box of water, so filled with water molecules, and then nonetheless in the IR, as you zoom out, it would flow to some kind of like relativistic field. And so this is the general description of quantum field theory. And when you go to the IR, when you go to infinite distance, basically by definition, you're getting a scale invariant quantum field theory. Because the whole idea is that you kind of scaled out infinitely. And so scale invariance is pretty much guaranteed in the IR. The thing which is not guaranteed is inversion. But it turns out that in almost every interesting scenario, if you have scale invariance as well as the usual rotation and translation invariance, you also have an inversion invariance. Thus, you also just have full CFT. So in most cases, the IR theory you get is a CFT. Now, this isn't all cases, and there's some weird exceptions, and like I think it's an interesting mathematical problem to see if you can prove that you always get a CFT in every possible context. But for most reasonable contexts, you get a CFT. Now, sometimes, of course, the CFT can be a trivial CFT, but you will almost always have conformal invariance in the IR. And so this is why CFT is so fundamental. So like it's not like it's not like, oh, there's many different quantum field theories, and for fun in this class we're studying ones with some weird symmetry group. Instead, this is really kind of foundational to what quantum field theory is. So let's give a couple more details about what I mean about flowing from the UV to the IR in a quantum field theory. So when you have a quantum field theory, oftentimes you write down an action for the theory with some Lagrangian L, and then you can add to that Lagrangian L operators. So let's write some abstract operator O with a coefficient G. Now, we want, of course, this whole quantity to be dimensionless, because dimensionful quantities don't really have any physical meaning. And so in order to do that, you want to define a dimensionful coupling, which we define, let's call it G bar, to be some length dimension, which we will call mu, to the power delta minus d times this original G. So d is the space-time dimension, which is the dimension of kind of the entire action. And delta is how this operator O, like its dimension. And so if we want this whole thing to be dimensionless, thus we define this new dimensionless coupling G bar. And so now this is a physical quantity, because of course dimensionful quantities aren't physical. You could just change them by some arbitrary human new definition. And so now let's ask what happens to this physical quantity G bar as we change the length scale, where the length scale is parameterized by this mu. So in particular, when we're going from the UV to the IR, we are going from mu equals infinity to mu equals 0. And so as you're changing the length scale in a quantum field theory, all the parameters in the quantum field theory are going to change, or not all, but most. So for instance, this delta, which says how this operator O changes under scaling, that delta is going to change under this flow from mu equals infinity to mu equals 0. So as I mentioned a moment ago, in the IR, the theory is scale invariant by definition, which we assume to also imply conformal invariance. And so once we get to the IR, all the quantities in this quantum field theory, such as delta, are going to be frozen to some specific value. So now let's ask the question of, there seems to be something special if delta is bigger than d or not. And so the obvious reason why it's special is that if mu is becoming very small, then if delta is bigger than d, so in the case of delta bigger than d, and we're taking the limit mu going to 0, which is how we define the IR, so in that case, this G bar is becoming small. Yes?
Shai, you shield the part of your blackboard by your body.
Okay,
so
okay.
could you stand somewhere?
Okay, I can also stand on the side.
Yes.
Okay, yeah, so let me know if it's visible. So in the case where delta is bigger than d, and we're going to the IR, so we're going to very large length scales, then you see that this coupling is becoming small. Conversely, if delta is smaller than d, then you see that the coupling would become big. And so we call operators with delta bigger than the space-time dimension relevant, or sorry, irrelevant. We call operators where the scaling dimension is smaller than the space-time dimension relevant. And so the reason why we call them relevant, irrelevant, hopefully should be obvious, because in the case where they're irrelevant, the coupling is basically going to 0, so these operators just don't matter. In the case where they are relevant, the coupling is becoming quite large, and so these operators certainly do matter. And so this is kind of the most, I guess, important distinction and importance of the scaling dimension of an operator, like whether or not it matters in the IR or not. So let's give a practical example in the context of the simplest possible quantum field theory. So we can write down the action for a theory which is invariant under a Z2 symmetry. So we're going to have fields phi, and our symmetry is that phi is going to go to minus phi, which is the simplest possible theory. So let's write down this Lagrangian. So we could have some kind of kinetic term. This is, of course, invariant under phi going to minus phi. And then we basically can write any polynomial in phi as long as it's even polynomial, such that it's symmetric. So we can have a term like phi squared, we can have a term like phi to the 4, and many other terms, which I won't write down for the moment. So with these terms, we should write their couplings. So here we would put mass squared, and then here, this is just conventional, we put some coupling G. And then I'm not writing the other guys just for simplicity. So these couplings M and G, these are just examples of the general couplings G I wrote down there. You can think of that we are deforming a free theory, which would just be this term, by these two operators with different couplings. And so these couplings, M and G, are both dimensionful, because in the UV, you can just count the dimension of an operator phi by just seeing that it adds up to the spacetime dimension D. So in particular, in the UV, delta of phi would just be D minus 2 over 2, which we can read off by demanding that this guy have the dimension D. And so just using this rule in the UV, you see that clearly, M squared and G are both going to be dimensional. But there's a dimensionless ratio which we can define, which is G squared over M squared. And so this guy is a dimensionless ratio, so it's some physical quantity, so it's something we can choose to dial when we are defining this theory. So the first question we can ask is this quantity positive or negative? So this is something which we can in principle choose. And if this quantity is negative, then if you look at this potential, so let's say this is our potential. So this guy is our potential as a function of V. And so we can just ask, does this potential have a minimum? So if this is negative, then you can just find the minimum of this potential, and you find that it has a non-trivial value. So basically, you just take the derivative of this and you solve, and you find that there's a minimum of the potential at some phi 0 equals square root minus 6 m squared over G. And so this means that in that vacuum, you would be breaking the Z2 symmetry, because you've basically chosen some special value of phi, which is the specific real quantity, assuming this thing is negative. If this quantity is positive, though, then you don't have this minimum, because this thing would be imaginary, and so then your minimum would just be 0, and you would preserve the Z2 symmetry. And so we can think of these two cases where G squared over M squared is negative versus where it's positive as two different phases. One which preserves the Z2 symmetry, and one which breaks the Z2 symmetry. And this is something we can just see just based on very general grounds, without doing any kind of complicated calculation. So because there are kind of two regimes, there must be some intermediate regime. And so I'm not going to say what the precise value of G squared over M squared is, but there must be some value such that you go from one phase to the other phase. And so where you have that phase transition, there you are going to have a non-trivial conformal field theory. Non-trivial in the sense that it's not just like an empty theory with no operators, or it's not just a free theory, it will be some interacting conformal field theory. And so what do we know about what's going to happen at this conformal field theory just based on general discussion? Well, the first question we want to ask is what are the operators that will be relevant? So, a first estimate would be to ask, well, what operators are relevant in the UV? And so if we focus, let's say, on d equals 3 for concreteness, then, so this operator, it's going to have 3 minus 2 over 2 times 2. So this operator is going to have 1. This is all in the UV. And then this operator is going to have 2, because it's just twice that, also in the UV. So both of these operators are definitely relevant in the UV. Now, are they relevant in the IR? Because the IR is the interesting non-trivial CFT we are attempting to study. And that is a strongly coupled question. So that's not something we can just immediately read on. But one might, I guess, that at least there'll be a couple of relevant operators, perhaps even 2, as we observed in the IR, or perhaps less. But that's something which isn't obvious. You have to actually compute them. Okay, so now we can talk about a slight generalization of this theory. So instead of just having this field phi, which is could be either positive or negative, we can imagine giving it an index I, where I goes from 1 to n, and then you just write down the exact same Lagrangian. Just now there'll be sums over I everywhere. We imagine that there's a big sum over I. And so then this theory, instead of having a Z2 symmetry, it has an ON symmetry. Because basically you have n different phi's and you can rotate them as a vector. And so this very similar analysis applies. I mean, you can also ask about this potential, and you can also say that when it's negative, you have something that breaks the ON symmetry. When it's positive, you have something that preserves it. And then again, there should be some intermediate value where there should be an interacting ON invariant CFT. So the reason why I mentioned this generalization is that, first of all, it's the simplest possible generalization. And also, both this Lagrangian as well as the generalization in this case have physical applications. So for instance, when n equals 2, this O2 invariant theory describes quantum phase transitions of thin film superconductors. And so this is, perhaps surprising naively, because I said how conformal field theories have, this Poincare group as well as scaling and inversion. And so you might think that's some kind of condensed matter system, why should that be a relativistic quantum field theory? And generically, most condensed matter systems are not relativistic, but nonetheless, when they undergo these phase transitions, they tend to, second order phase transitions in particular, they have an emergent relativistic spacetime symmetry, and in addition, scaling and inversion, so they are a full conformal field theory. So that's an example of a physical application. Of course, the case of n equals 1, which is the Z2 symmetry, that's the Ising model, and that has many physical applications. So something which is interesting is that CFTs describe not just quantum phase transitions, as you might expect from a quantum field theory, but they also describe phase transitions of classical statistical field theories. So in classical statistical field theories, there is no quantum mechanics. So because thermal fluctuations suppress quantum fluctuations. And so to give you the simplest possible example, I will introduce the Ising model, which is the simplest statistical field theory and just the simplest field theory in general. And so I want to emphasize here that this description does not make use of quantum mechanics at all. This is just statistical physics. So you can find the Ising model by just writing down its partition function, which is a sum over lattice sites, Si, and then you have an exponential. You have some coupling J divided by temperature T, and then you're summing, this means nearest neighbor. And so you're summing over, so these S's are called spins. And so you imagine that you have some kind of lattice, and at each point on this lattice, there live these spins. And then so this is the Hamiltonian of the theory, and it says that basically if you have two adjacent spins, which have either like the same value of S or opposite values of S, then this affects the value of the energy, and then you just sum over all possible configurations, and that gives you the partition function. And so just to emphasize, this is really the simplest field theory, like in the world, you know. And so for this extremely simple model, you can describe, and this is a statistical model, you know, we're not using quantum mechanics here. So you could define the correlation length as just the 2-point function of spins. So Si, Sj, the simplest correlation function of these operators S, statistical operators. So this takes the form I minus j over some c. And this is the case as the distance between the spins becomes big. So this is the generic case of what you expect for correlations between spins. So this is how you expect like one part of the system to affect the other part of the system as you look at very different parts when they're very far away. This is what you would expect generically. On the other hand though, here you have these parameters, j and t, and their ratio is dimensionless. So just as before, we were tuning the ratio of g and m in that 5 to the 4 theory, analogously here, we can tune the ratio of j and t. And so there's kind of a similar idea where like when the ratio is positive, you get something which breaks Z2 symmetry, where Z2 symmetry in this case is just S going to minus S, analogous to there. And when J over T has the opposite sign, then you preserve the Z2 symmetry, and there's some intermediate value where there is a phase transition. So at that critical value of J over T, which I'll write like this, so there's some special value where you're going to have that this C, which is what you call the correlation length.
So in this case, J over T always has the same sign, right? J in ferromagnetic case, J will be positive.
Sure. Yeah. Okay.
It's not a sign; it's just a value of J.
Yeah. Sorry. Yeah. So the analogy is not clear. This is a good comment. Yeah. It's okay. It's more just like there's a special value of J over T where you have a second order phase transition. It's not the sign. It's more just the absolute value. Yeah. Thanks for the comment. Anyway, so here. There's some special value of J over T, which we call the critical value. So in particular, there's some critical temperature C, such that this C is going to go like this. So it's going to diverge as you tune the temperature to be near the critical temperature. This is a nu, not a 2. Hopefully that's clear. So as you get very near the critical temperature, you find that this correlation length, which is basically an estimate of how very far away things affect each other, according to this equation, you find that this thing starts diverging with a certain power law. And so that also implies that you're no longer going to have this exponential dependence for correlations between spins. You're also going to start having some power law dependence. And so what's happening physically? What's happening as you go to the critical value of the temperature and the coupling is that the entire system starts interacting. So it's no longer the case that like one spin here and one spin all the way over there, stop affecting each other. Now all the spins are affecting each other. So basically you have emergent scale invariance. And so, this is basically why you get a CFT, because scale invariance is emergent, you also have an inversion invariance. So far I wrote this as a lattice, but in this limit.
Sorry, can I ask a question?
Sure.
So, just to give a background, so I'm a physicist.
Sure.
So
yeah.
There are in fact phase transitions where you can write down some theory for it, but it's not relativistic. But it can have critical exponents and things like that. So,
yeah.
So I'm just asking. So in your case, when you talk about CFTs, you also not only do you want it to be scale invariant, you also want to have underlying Lorentz invariance. Is that correct?
Yeah. So it's a good comment that there are examples of phase transistors which are described by things called Lifshitz, fixed points.
Yeah, and even in the superfluid example you gave, you can have corrections to that action which have just one part of T, and it's like some dissipative term, so it's like mod omega or something like that. And you can work out all the exponents and stuff. Yeah. But you wouldn't probably have a CFT disk.
Yeah. So I wouldn't call that a conventional conformal field theory. I think the technical term is like a Lifshitz theory, and it's So like there are I don't know if I should use the term exotic. There are other cases which are not described by what we're going to be discussing in this class, which is standard conformal field theories, where you have a phase transition, but the scaling works a little bit differently. So you don't have like kind of standard scale invariance. You have some kind of modified scale invariance. But so we're not going to be discussing that in this class, but indeed those are very interesting and they show up in condensed matter examples. But there are also many condensed matter examples which are described by the vanilla CFTs. And so those are the ones we're gonna be focusing on for this class. And it is a very interesting question about how you can use maybe tools related to conformal field theory to perhaps try to describe those, but that's gonna be beyond the specific class. Okay, thanks for the good comment. So anyway, so back to this just simple Ising model. So this started off as a lattice, but in the limit where we are approaching this critical value of J over the temperature, because the whole system is interacting, we can take a limit where we replace these discrete spins Si by some continuous variable sigma. So instead of having an index I, which is discrete, you now have some continuum variable x, and then sigma is just S promoted to being this field. So this is a field because it's a function of spacetime by definition. And so now, instead of having this 2-point function of these Si, Sj's, you can now consider a 2-point function sigma of x, sigma of y. So this is in this continuum limit. And then here, at this critical point where this correlation length diverged, you now find that this 2-point function, it's no longer is exponentially damped because this thing was diverging. So now you could just work it out, and this is x minus y to the d minus 2 plus eta, where this eta is different from nu. So, and this eta in general is another interesting physical quantity which you have to compute. And so the dependence on x and y is fixed just by symmetry. D is the spacetime dimension, and eta is another interesting quantity. So this eta and this nu, these are called critical exponents. And these critical exponents are the things that experimentalists who are studying systems and phase transitions that are actually described by CFTs, these are the things that people are actually measuring. Because you can measure the correlation length in some condensed matter system and then read off this value of nu. Similarly, you could measure how one spin affects another spin, I think, and read off the value of eta. And so these are things which experimentalists actually have predictions for. And they're very non-trivial numbers. The answer usually isn't just 5. It'll be some kind of basically probably transcendental number. But who knows? Okay, so far we've discussed 2 systems. The first one was phi to the 4. The second one was this Ising model where it started off as a lattice system, but then we took the continuum limit where it is now another field theory, which seems to be described as CFT. We're going to describe one last system. And so the last system we're going to discuss, which hopefully people can see, is probably the simplest system of all, which is just water-vapor phase transition. And so this is something we observe every day. If you have a glass of water and it starts evaporating, because it's hot outside. And so in this case, the UV are water molecules. And so the UV is incredibly complicated. It's trillions of water molecules in a glass of water, which are all interacting in super complicated ways. So the UV is way more complicated than this system and that system. Because in this system, the UV was just this, lattice, and in that system, the UV was just, the simple field theory. Whereas this, UV, you would have to be a supercomputer in order to understand it. And even then, it's probably impossible. And so the parameters which you use to discuss this system, kind of the statistical parameters, because of course you can't describe the momentum and position of 1 billion water molecules. So instead, you use things like, so let's say the volume is fixed, so you would have the pressure and the temperature. And so then, if you're some experimentalist or just a regular person and you have your bottle of water, you can vary the pressure and temperature of that bottle of water, and you will find that there's some special value, let's call it critical, of the pressure and the temperature, such that this system undergoes a second-order phase transition. And so as a second-order phase transition, it turns out this guy is also described by a CFT. And so there's even something called critical opalescence, which is something you can look up on YouTube, where you can actually physically see that water becomes milky once the pressure and temperature are tuned to this very special value. So this is a case where you can actually see a CFT. Okay, so we've described 3 different systems. In the UV, I really want to emphasize that these systems are completely different. They couldn't be more different. And yet, nonetheless, and I guess many people in the audience already know this, but the big reveal for those who don't is that these are all the same CFT. And that's something which should really surprise you, because why should it be that systems, which are so incredibly different in the UV, this having billions of particles, this being some lattice, this being some field theory, why should they all become the completely identical system in the IR? And by identical, I mean completely identical. So every single physical observable you compute in the large distance limit, which is what the IR, will be completely the same. Where physical quantities include what I call these critical exponents, eta and nu, In this case, what I described as the scaling dimensions, which I'll relate in a moment. So all those things are just exactly the same in the IR. And so this is an extremely surprising fact. A term which is sometimes used for this is called universality, where it's the fact that you have many different things in the UV and they all become the same thing in the IR. And so one of the things you're going to learn in this class is why that's true and how you can actually compute things in these CFTs. But first, let's give kind of a hint of why this surprising fact might be true. So why universality? And so we can use the intuition we learned about relevant operators to try to explain this. Because remember we discussed just 20 minutes ago about how when you go to the IR, you could basically say whether or not adding an operator to the action matters or not, depending on whether or not a scaling dimension was bigger or smaller than the spacetime dimension, which say is 3, for many physical examples. So the first fact is that the number of things you need to tune to get to your CFT, this equals the number of relevant operators under the UV symmetry. So for instance, in this UV system, it had Z2 symmetry in the UV, and so it turns out there's just going to be one relevant operator in the IR, which was invariant under the UV symmetry Z2. And that's why you only have to tune one parameter, which is the ratio of this J over T. It would have been 2 parameters if you would have allowed coupling to some external magnetic field. But here we just said that's 0. Similarly, in this system, the UV Lagrangian we wrote down was, by definition, invariant under the Z2 symmetry. And again, one can find that there's only one relevant operator, which is invariant under Z2. So that's again why you only had to tune one parameter, which was this ratio of G and M. In the case of a bottle of water, of course, the UV has no symmetries because it's totally random. And that's why you have to tune more parameters. So it turns out that there are only 2 relevant operators in general in the CFT these guys are all flowing to, and that's why you have to tune 2 parameters, pressure and temperature. So one aspect to the answer of why universality is that CFTs have very few relevant operators. And so right now I'm just telling this to you as some fact, so you shouldn't necessarily believe me. But one of the things we're going to learn in this class is that we're actually going to find that CFTs have very few relevant operators. They didn't have to be the case. Like there could have been CFTs with like 1 billion relevant operators. Okay, so this is one fact. The second fact is that if there is a unique CFT, so if you could show that there's a unique CFT with Z2 symmetry, and just one Z2 even and one Z2 odd relevant operator.
And does it also depend on the fixed point, how many operators you need to fix? Because for example, in 5 to the 4 0, you have like a free fixed point when you need to fix M squared and G squared, and there is like Ising.
Well, there can be a free fixed point, but I was assuming you're tuning G over M such you get to the interacting fixed point.
But it doesn't say that you have on the one that relevant operator, you can have like 2.
Well, okay. So the number of relevant operators is an IR question and it's strongly coupled. So I haven't proven to you that there's like only 1 or 2 or even 5 relevant operators in the IR. Right now I'm just assuming that. So that's a strongly coupled question. So it's a hard question. So that's one of the things we're going to learn in this class, how you can show that. Right now I'm just assuming that there's a certain number of relevant operators. And if you have the same number of relevant operators, and with the second assumption number 2, that there is a unique CFT with only 2 relevant operators, one Z2 even, one Z2 odd. So if you assume those facts, which are just assumptions so far, then this would prove that all 3 of these systems have to be the same CFT.
So Shai,
Yeah.
the number of parameters to tune, that's the number of relevant operators in the IR theory, not in the UV theory.
No, but it's the number. But you count how many of the relevant operators in the IR which were invariant under the UV symmetries.
Yeah, but the number of parameters to tune is really the number of parameters.
Sure. Yeah. The number of parameters to tune is ultimately an IR quantity, but it's also related to how many of them were invariant under the UV symmetry. So the UV also does matter for this question. That's why, for instance, for water you have to tune 2 parameters, whereas for this system or 5 to 4, there's just 1 parameter you have to tune. And so, in real physical systems, oftentimes the UV doesn't have any symmetries. Although there's special cases where it does. So in some superfluids, you might have some O2 symmetry due to the wave function always having an exact O2. But so certainly for water vapor, you don't have that. And so if this is true, this basically proves universality. And this also is kind of like another example of how special CFTs are. That this question of how many relevant operators, it turns out there's a very restricted class of CFTs with just a few relevant operators.
Sorry, could you repeat the second one? I didn't understand. What's so special about Z2? Why can't you have some other discrete symmetry?
I'll just give you an example. Yeah,
Oh, I see.
yeah. So this is just the simplest example because like Z2 is the simplest symmetry group. And so like, if you're talking about systems which don't have any symmetry, such as water vapor, you would say like at a minimum, maybe at most, they would have an enhanced Z2 in the IR. In some cases they might have more, like the ON model. But I'm just saying that like if you could prove this fact, then you would have proven that these systems all flow to the same CFT unless there's somehow magically some enhanced symmetry in the IR.
And so in the water case, that Z2 is really an accidental symmetry.
Yeah. It's an accidental symmetry. It's basically related to the fact that there's no 3D CFT with no symmetry. Which is an interesting question. I mean, like, because like in 2D there are such theories, and in 4D there are such theories. Well, it depends. There's supersymmetric theories, and in some sense, okay, in some sense there are such theories, but in 3D, as far as we know, there are no such theories. Okay, so I described 3 different UVs that all flow to the same IR, but the UV can be, really anything. It can be even something really crazy, So like it could be in quantum gravity, the UV could even be things we call brains. Which maybe many people in the audience don't know what those are, but assuredly they are not water molecules. And nonetheless, these bizarre brains that we have with quantum gravity in the IR can again flow to a CFT. And so that's not just kind of some exotic example. This is a hint to something called ADS CFT, which is the statement that quantum gravity in anti de Sitter space, which is negatively curved space-time, is related to a CFT in one less dimension. And so this is, as yet, our only non-perturbative way of studying quantum gravity. And this is another reason why we care about CFTs. So CFTs, they not only describe second-order phase transitions in condensed matter, they not only are useful for computing cosmological correlators in cosmology, but they are also probably the only way we have of understanding quantum gravity. So that's another motivation, although in this class, I'm not going to go into that so much because it's beyond the level of class. Okay, so hopefully I've convinced you that CFTs are interesting, and I've given you a little bit of an introduction. And I've also explained how they have more symmetries than conventional quantum field theories. And so this might make you think, if they have more symmetry, that they would be easier to study. Yet it turns out, in fact, that they are not easier to study than your average quantum field theory. And the reason is because of strong coupling. So this is really kind of the villain of this class. Or the hero, I guess, if you like to do hard calculations. So strong coupling is the fact that these coupling parameters, M and G, in most interesting CFTs, in pretty much every interesting CFT, they are not small numbers. And so the way people usually study things in physics, or even science in general, is that you try to do some kind of perturbative expansion around something you understand completely. So for instance, when you take your introductory quantum mechanics course, you do perturbation theory, and so you're perturbing in some parameter which is hopefully small. So if you've taken quantum field theory, you will have done perturbation theory probably in alpha prime, or whatever, alpha, the spine structure constant, which is 1/137. So this is a fairly small number. And so if you compute Feynman diagrams as an expansion in alpha, there's some expectation that the answer should be pretty good. But the problem is that in conformal field theories, the analog of alpha, so what you might call M and G here, it's never small, usually. And so that's why you just can't do perturbation theory, it doesn't work. So you write down Feynman diagrams and they're basically useless. And so that's why it's very hard to study conformal field theories, because they are strongly coupled. And so we have to find some way to get around the fact that the couplings are not small in conformal field theories. And so this problem has been, attacked over the years in many different ways.
Just lowers the blackboard.
Sorry?
Just lowers the blackboard.
Thank you for the suggestion. So what are some ways that people have tried to get around the fact that the couplings are all big? So one method was to find other parameters in the system that you could use to get a perturbative expansion. So I mentioned how there's a generalization of this system where you have n different phis, and this has ON symmetry. So you can consider the limit where n is big, and it turns out in that limit that the theory basically becomes, weakly coupled in some sense, and it allows you to compute things as an expansion in one array. And so this is very useful if you want to study the O abelian theory. But unfortunately, the theories that are of interest to condensed matter are not O abelian, they're usually O1, O2, O3. And of course, there's no reason why O abelian should give you any insight on O3. So that's kind of the problem with this. There's kind of a related non-rigorous method, which is called the epsilon expansion, where basically you fix the space-time dimension to be 4 minus epsilon, and say your goal is to study the 3D Ising model. And then you very boldly extrapolate epsilon to be 1. And so this is what Ken Wilson and Fisher famously did in their paper, the Ising model in 3.999 dimensions. So it's a very clever trick, and it actually gives an estimate which shockingly is like not that far off from the right value. But of course, this is also completely unjustified. So these are both asymptotic expansions and unjustified expansions. And so, look, they were the best we had for many years, which is why we did them. But like, hopefully we could do better than these unjustified analytic expansions. So a method which is probably on much better footing is basically to consider your lattice problem, such as the lattice Ising model, and just put it on a computer. So truncate the number of sites to some finite number, and then study it using methods such as lattice Monte Carlo. So you could just describe this as lattice numerical methods. And so this is, a very powerful technique. It's very popular in the condensed matter community. And the problem with this method of the lattice is that if specifically you're trying to study the critical point, then that's where it is hardest for the lattice to access. Because that's the point where, as we just described, this correlation length is going to infinity. So the entire lattice is all interactive. And so like once you truncate it to some finite number of spins, it's not guaranteed that's gonna be a good approximation. And so you have to take a lot of unjustified extrapolations of like the size of your system and the size of your lattice spacing. And so nonetheless, very hardworking scientists have managed to push these lattice methods such that they have estimates. But also, it also doesn't even work for many interesting CFTs. So for the simplest CFTs like the Ising model or ON models, in principle you could study using the lattice. But once you start introducing field theories that have fermions, you have something called the sign problem, and then people just can't use lattice at all. And so that's why, this method, even though it's non-perturbative in principle and very powerful, has inherent limitations. So the last method is the bootstrap, which is the hero of our story. And so this is a method which was developed, well, I guess I can't say so recently, because at this point it's been like 15 years, but in the scheme of things, I would say fairly recently. And this method, as we will discuss over these lectures, inherently uses conformal symmetry. It is numerical, like lattice, but it's also rigorous in a sense that will be explained. And so it is rigorous, and it actually gives, in practice, better estimates than lattice, and certainly than large N or the epsilon expansion. So just to give you an example, so let's consider the CFT we've discussed so far, this Ising CFT, which described water vapor, phi to the 4, as well as the Ising lattice model. So we have Monte Carlo, the epsilon expansion, and bootstrap. And let's discuss how they were used to estimate the two simplest quantities, which is the scaling dimension of sigma and the scaling dimension of epsilon, where in the context of phi to the 4, sigma is just defined as phi, and epsilon is defined as phi squared. And as we will learn in this class, it turns out that these are the only two relevant operators. So this one is E2A, this one is E2E. So these critical exponents, or scaling dimensions, have been estimated using these different theoretical methods. It's a little bit higher. And so for Monte Carlo, you get 0.51813 and 1.41275. Using the epsilon expansion, you get 0.5182 and 1.4139. So you see it's a little bit less accurate, although it roughly agrees. And then finally with the bootstrap, this is as of 5 years ago. So actually there's much better estimates at this point. But at least when I wrote these notes 5 years ago, the best value, 1.181489 and 1.412625. And these numbers are all rigorous, as will be explained in this class. So as you can see, like the level of accuracy is orders of magnitude more accurate than lattice, and completely blows epsilon expansion out of the water. And these have actually gotten much, much better, as I'll explain later on in the class. And so this is a practical demonstration that this method really works in the simplest possible example, and in fact, it's been used in many more complicated examples since then.
So this is for D to 3.
And this is in 3D. This is for the 3D Ising model. Because of course, the 2D Ising model was already solved many years ago, and the 4D Ising model is
What
not
about
so
the
much.
40?
Sorry?
I want to ask, what about 40?
Well, in 4D, there is no non-trivial interacting CFT. So in 4D, everything just flows to the free point. I mean, that's basically related to the fact that this phi to the 4 term is like, marginal in the UV when D equals 4. It has dimension 4. So the interesting example really is 3D, and that's where really these studies were done. Okay, So that concludes kind of the general introduction. And so now we're going to get into some details about conformal symmetry and how it's used to constrain quantum field theories. But before we jump into that, any questions about this, I guess, very general introduction? Also from the Zoom. Also, people might be asking questions on the Zoom.
I have a weird question. So these critical exponents for the water vapor phase transition, you can also just do an experiment and measure,
Experiments have also been done, but this is a theoretical class, that's why I did not write the experimental level.
what.
But
You don't know.
they do, I mean, look, experiments are hard, and so I think the number of digits which we have experimentally is fewer than these, although they do roughly agree. I mean, I guess this is one reason why Wilson won a Nobel Prize. So, I mean, look, epsilon expansion does work, at least in this simple case. Cool. Okay, great. And so this concludes kind of the very general introduction. And so now let's actually
You
discuss.
can also lower.
Sorry.
Work.
Thank you for the reminder. Okay, so let's discuss how conformal symmetry actually constrains quantum field theories. And so let's start by just defining the conformal group. So the conformal group, it could just be the list of translations, rotations, inversions, and scaling, but let's give a more, a different definition. So maybe even somewhat a simpler definition. You could say it's just any change of your spacetime point, x to x prime, which preserves the metric up to an overall position-dependent rescaling. So to make that precise, the new metric at this new point equals just some overall scaling, this omega squared of x, times the old metric. So another way of saying this is that conformal symmetries preserve angles. And it turns out, you'll see in a moment, that this is equivalent to the 4 elements of the spacetime group, which I discussed before. But this is kind of the most elementary mathematical definition of what the conformal group is. So this is kind of like how mathematicians would study. And so in order to learn a little bit more about this group, the next thing we can do is that we can assume that this new point x is just a small perturbation from the original point x. So we assume x prime is just x plus some small epsilon as a function of x, and we just plug that into this equation, expand in epsilon, and you will find that in this approximation, this thing now equals it now equals g mu nu of x minus delta mu epsilon nu plus delta nu epsilon mu, plus some smaller terms. And so this means that in order for your theory to be invariant up to this omega x, it must be the case that this quantity, which is called in conformal killing vector, that this thing has to equal the conformal killing equation, which is that this quantity has to equal 2 over d rho epsilon rho. And so this just literally follows from just expanding an epsilon, and then you can take the trace of both sides to see that it has to equal this. And so basically omega squared equals this quantity on the right-hand side after you took the trace. And so there are 4 solutions to this conformal killing equation. So we're talking about the conformal group infinitesimal. So the 4 solutions to this equation.
Here you assume the initial metric is delta Euclidean, right?
Yeah. So we're expanding around the Euclidean metric. Okay, so that's an important comment. I'm doing everything for the Euclidean conformal group just to make life easier.
No, I meant that it's delta. You really assume that it's delta, right? Otherwise it would be.
Yes.
Covariant derivatives.
Okay, so the 4 solutions to this conformal killing equation are so either epsilon mu of x, so it can be a constant. This will be a translation. Just in the obvious sense that you're just moving x by a constant, so that's why it's a translation. Another solution, if I'm going to keep writing this, another solution is that it can be a rotation. So you'll have some infinitesimal matrix m mu nu, which is rotating your position x. Another solution is a dilation. We have some overall alpha, which is multiplying x mu. And I mean, it's very easy to check this. I mean, you can even probably do this in your head, that this equation is satisfied by these very simple solutions. So this is called a dilation, which is basically scale invariance. Some people like to call it dilatation, which I never understood why. I think dilation is much more elegant. And then there's another solution. This is kind of the funky one. This is x nu b nu. So there's a parameter b, x mu minus b mu x squared. And this is called a special conformal transformation because I guess there's no better word for it. But you know, to give some intuition of what this ugly guy means, all this thing is so you can write it like this. You could say that x prime mu over x prime squared equals x mu over x squared minus b mu. So this is the finite version of this. So this is when you're doing an infinitesimal transformation, and if you do a big one, then the transformation looks like this. And from this perspective, it should be clear what this thing is. So as you've done an inversion, then you've translated by b, and then you did another inversion. And so that's why this guy is really it's like translation, inversion, translation. And so because you already had translations here, like the novelty here is really inversions. And so that's why, kind of morally speaking, I would think of this as an inversion. Although the reason why it's not literally an inversion is that an inversion is a discrete symmetry, and these are all supposed to be continuous. And so that's why it's an inversion kind of combined with the translation. Okay, so
Excuse me, I think it's inversion, translation inversion.
it's invert. Yeah, sorry. Say the opposite. I think it's inversion, translation, inversion. Okay, sorry. Thanks for correcting that typo. So yeah, it's an inversion followed by translation followed by inversion. And so these are the four. So as advertised, this is what makes it the conformal group. It's these three kinds of space-time transformations. And so these are infinitesimal, but aside from this guy, the finite version is obvious. This is finite rotation, finite rescaling, and finite translation. Okay, so now let's ask, how do these transformations, now that we've derived them, how do they act on some function of position? So let's say that we have some function of x, which is going to a new function of x prime. We're doing these transformations where like these parameters, let's say like m, alpha, or b, we're assuming they are small. So let's call that parameter a in general, and let's assume that it's small. And so for some small transformation parameter a. So in that case, we can define the generator of this transformation g, and this is just the usual way you define things in group theory. It's just the parameter which is small with f prime of x prime minus f of x. And so this is the definition of a generator of that transformation. And so based on how these transformations act, as given here, you can then just write down what the generator would be. So from a more mathematical perspective, you could say this is like the generator in a specific representation, but I'm using this representation I think is simplest, and that's in terms of differential operators. And so the generator we get for the translation is simply a derivative in terms of b. And so this is just so if you have a function and you expand, instead of x you now have x plus a, and then you expand for a small, of course, doing a Taylor expansion, you're going to get a derivative of it. And that's why the generator is just the derivative. Similarly, if you do the same exercise for a rotation, you will find that the generator is x mu d nu minus x nu d mu. You can do a similar exercise for scaling. Then you're going to find that it's a contraction between x mu d mu. And then finally, you have this funny guy, this special conformal transformation. And here it's 2 x mu d mu x minus x squared d mu. So the names we give for these different generators, this guy is called P, this guy is called M, this guy is called D, and this guy is called K. So this is just the convention which are used for these generators in the literature. This has an index, this has 2 index, this has 1 index, this has no index. Okay, and so now that we have written down the explicit generators in this representation corresponding to the 4 elements of the symmetry group, the last thing we want to do is find how they commute. Because usually the way you define a group is you need to know its commutation relations. You want to know its algebra. So it's a fairly straightforward exercise to work out what the algebra will be based on the fact that we have explicit representations for these generators, because you have them written in terms of these derivatives. So you can just apply them to some test function like f, and just commute them, and you will find the following algebra, which I'll write this kind of schematically, so as to save time. So the algebra between m and p is basically a delta function p minus another delta function p. So I'm not writing all the indices. You'll find them in the notes. Sorry.
Connected delta.
Quadrant delta. Yeah. Sorry. Well, maybe I'll write the indices this one time. Mu rho nu, and this was mu nu rho. And so all this is basically saying is that this is in algebraic terms the fact that this quantity is a vector. That's what it means that it commutes with m in that way. And so for m and k, you basically get the same thing except with k's. And this is also just saying that k is a vector. So not so interesting. For m with itself, you get a more complicated quantity involving a whole bunch of m's, but all that's saying is that m is the definition of like a rotation algebra. So the part where it gets interesting is when you write down the commutator between k with p. So in that case, you get, so here I'll write it more carefully. You get 2 delta mu nu d minus 2 mu nu. And then finally, this one's also interesting. So d with p mu just gives p itself, and d with k gives minus k. So let's interpret what is meant by these things. So first of all, you can show that this whole conformal algebra, so the conformal group, turns out it's isomorphic in d dimensions to the group SOD plus 1, comma 1. So as a reminder for those who maybe aren't so familiar with group theory, so SOD is the group of rotations in d dimensions. So if we didn't have dilations and special conformal transformations, then the rotation group would just be literally SOD. So that's rotations in d dimensions. Once you add these other elements, it turns out the group is enhanced to SOD plus 1, comma 1, and you could show that isomorphism just by taking this M, P, K, and D and rewriting it such that it satisfies this algebra, except now in D plus 1, comma 1 instead of just D. And so that isomorphism is pretty easy to show. I mean, basically, P plus K is just an extra element of the rotation, D is another element, and then M was everything for SOD. So that's something you will show in the exercises for the lecture. So that's one interesting fact we see from this algebra. We should also ask how, so now that we've written down the algebra, we should ask how do these generators act on an operator in our quantum field theory? Because that's ultimately what we want to use conformal symmetry for. So first of all, we can ask how translations act. And so the way you see how a transformation acts on an operator in the usual group theoretic sense is that you exponentiate the generator and you act on it on your operator. So let's start with an operator evaluated at 0. And so if we act with the translation by conjugating it with these generators, then this, basically by definition gives O evaluated at this new position X. And so the infinitesimal version of this, if X were something really small, this would just be the statement that P commuting with O of X is a derivative acting on O of X. So this is how translations act on an operator originally at the origin. And so you could do a similar exercise for the other generators. So for instance, if you act with a rotation, all it will do is rotate the position of the operator. And the first interesting fact is that in this algebra we wrote down, you can see that D, which is the generator of the dilations, commutes with M. So I didn't actually write that down, but these are all the non-zero commutation relations. Everything I didn't write down are zero commutation relations. And so the fact that D commutes with M, so the fact that this is 0, this means you can diagonalize both D and M in some basis of operators simultaneously. And so that means you can assign, eigenvalues to both D and M at the same time. And so in particular, the eigenvalue of D with an operator evaluated at 0, this is basically defined to be the scaling dimension of the operator. So let's label the operator by delta. Then commuting with D gives the scaling dimension. So this is one label, which labels our operators. And then the other label, because M commutes with D, is just how the operator transforms under M, which is basically its representation under the spacetime group. And so you can say the other operator is the spin, which is just the usual eigenvalue for how an operator changes under rotations. And so these two quantities, scaling dimension and spin, are the basic labels for all operators in a conformal field theory. And so like if you know the scaling dimensions and spins of all operators, then you know completely how to describe each operator in the conformal field theory. And so the novelty here is really the scaling dimension, because for a regular relativistic quantum field theory, you would always have spin, but it's only for a CFT that you also have a scaling dimension. So the next thing we can learn about this algebra is the fact that D commuted with P gives P and D commuted with K gives minus K. So for those who have studied quantum mechanics with raising and lowering operators, you can see that basically P and K are acting as raising and lowering operators for the scaling dimension. So to see that explicitly, you can just commute D with P commuted with an operator at the origin. And just by using the algebra, you will find that this gives delta plus 1 times P commuted with the operator. And so here you saw that you raise delta by 1 by using P. And so if you do a similar thing with K, so this is D. I'm sorry, my handwriting's not that good. So if you do a similar thing with K, then you will find that this is delta minus 1 times K commuted with the operator. And so thus K acts as a lowering operator. And so you have raising and lowering operators given by P and K in this Euclidean basis. So we're not going to show it in this lecture, but it turns out that you can prove for unitary conformal field theories that there is a lower bound on the value of delta. So we're going to show that delta always has to be greater than or equal to some number. And so if we just assume this for a second, then if we act with enough Ks, and if delta gets smaller and smaller, at some point we're just going to kill the operator. And so in particular, we can define operators such that they have the lowest possible scaling dimension as primary operators. So in particular, we can define it as K commuted with O primary at the origin is 0. And this is the definition of a primary operator. And then given a primary operator, we can get what are called descendant operators by just acting with P. And so as you see, P raises the value of delta by 1. And so for every primary operator, there's an infinite family of descendants which just have dimensions bigger by integers, for every single integer. And so that's what's called the conformal multiple. And so because those are all related by symmetry, for the rest of this class, we're only ever going to talk about conformal primaries, because the descendants are all just kind of related by symmetry. And so the three things we've learned from this algebra is that we label operators by scaling dimension and spin, and that there exist conformal primaries, which are killed by K, and then all the descendants that come from those.
So in the bound, so the assumption is that its presentation is unitary and positive energy, something like that?
Yeah. So but we're going to discuss those aspects in the next. This lecture is mostly about kinematics,
Right.
and in order for unitarity, you have to study dynamics, and we're going to leave that for the next lecture.
So I want to also, not all operators can be labeled by delta and spin, right? I mean, I can always construct some operator where if I commute it with D, I'll get something complicated out.
Well, okay, so in a CFT, all local operators can be labeled by scaling dimension and spin. So you also have non-local operators, something like Wilson loops or Wilson lines, which indeed, cannot be labeled just by scaling dimension and spin. They require other labels. And also in a generic quantum field theory, this wouldn't be true either. So this is just something very special to conformal field theories, that you have spin and scaling dimension. So I was a little bit hazy about spin. Spin is basically the labels of the rotation group SOD. And so depending on D, you might have multiple labels. So for instance, if you're working in 3D, you would need the number of labels of SO3. In that case, it's just 1. So you call that J, and that's literally the spin. If D is bigger than 3, then there's multiple labels. So so in 4D, if you're labeling the representation of the Lorentz group in 4 dimensions, there's 2 labels. Sometimes you call it J left, J right, etc. But I was just calling all these labels collectively the spin. And for the purposes of these lectures, more precisely, I'm going to basically call spin like the rank of symmetric representations under SOD. So more precisely, spin is symmetric reps of SOD. So to give an example, like the stress tensor operator, this is rank 2. And so I would say this thing has spin 2. And then if you have some kind of flavor current, J mu, I would say this thing has spin 1. And then like an operator like, I squared, this has spin 2. Is that so I'm not going to consider like weird operators, which in principle you could have, say in 4D, which would have some kind of mixed symmetry under the SOD, such as like the field strength. So I'm not going to be considering that. Because it turns out they won't actually matter for the simplest calculations, which one might want to. Okay, so far we've discussed the algebra and how the algebra acts on operators, and we've said how you can label them by scaling dimension and spin, and that the conformal generators act as raising and lowering operators, and so the lowest possible operator is what we call the primary, and then we have infinite descendants. And so next, we would want to say how, so this is all coming from the conformal algebra, it's kind of like infinitesimally small transformations. But you might want to ask how do finite transformations act on operators. And so for that, the usual thing we do in group theory, another board, is we just exponentiate. So we define the finite transformation U as the exponentiated generator G. And so then we want to say how does this U act on some operator O, now at finite position. So this is acting with the finite generator on O. And so this is kind of like the most general constraint of conformal invariance. And so just to write it down precisely, so this is omega, which we introduced in the beginning. This is basically how the metric changed under the conformal transformation. And so if you act with this finite transformation on an operator, you get this omega to the delta. This is operator labeled by delta. You get this d acting on x prime. This is basically taking into account the fact that the operator can be spinning. So let's give it some label A, which is some label for the spin, like a very general label. I'm letting it have like spin. I'm just giving it a general label. And then, so this spin label will also be changed by the transformation. For here, as before, I define this omega to be how the metric changed. So this is how a finite transformation acts on an operator O in some general representation R of the spin group. So this is the most general constraint of conformal symmetry. And so, to give an example, like let's imagine that first of all the operator is a scalar, so we can forget about this d of R stuff. And let's also imagine that our transformation is just some dilation. So we're just changing x up to some lambda. And so if you just take this formula, apply it to a scalar, let u be e to the lambda x, then you will find that in this case you're now getting e to the d O of x e to the minus d equals lambda to the delta O of lambda x. And so this is how an operator changes under dilations. So basically it's multiplied by the variable lambda to the delta, and you also put a lambda inside. And so this is kind of intuitively how you would expect something to change under a rescaling. So you rescaled it, and then it depends on the value of delta. And then you can similarly do this for other things like translations, rotations, but I think kind of the most intuitively interesting one is this delta. And then if furthermore, if you were to make this thing infinitesimal, so if you want like a small dilation, if lambda is small, then you would just recover the formula out there of what a small dilation is. Okay. So this concludes how conformal symmetry acts on operators. So this is kind of the kinematics of conformal symmetry on a given operator. But the quantity we care about in quantum field theory and quantum mechanics for that matter is correlation functions. So we want the expectation value of many operators. That's kind of the main thing we care about. And so now in the final thing we're going to do in today's class, let's discuss how conformal symmetry constrains correlation functions. So the first thing we can talk about is a one-point function. So how is a 1-point function constrained by conformal symmetry? Very easy, 0. Why is it 0? Because there's no scale in a conformal field theory. So if this thing was non-zero, that would define a scale, and it couldn't be conformally invariant. I mean, you can also just derive this by just like acting on this 1-point function with transformations and just seeing that if it was anything non-zero, it would violate conformal symmetry. Okay, so that's easy. So 1-point functions are easy. Next, we can look at 2-point functions. So for simplicity, let's just look at 2-point function of two scalars. And so we want to know how this thing is fixed by conformal symmetry. So first of all, because it's translationally invariant, we know that whatever this answer is, it has to depend on like the difference between x minus y. And then because it's rotationally invariant, we also know that it must depend on the magnitude of the difference of x minus y. So this is what we know just if there's a relativistic quantum field theory. But based on the fact that it's a conformal field theory, it means that we can furthermore fix it. So under scale invariance, we can show that this function of x minus y is actually uniquely fixed. So it has to be 1 over x minus y 2 to the 2 delta. Or also, like, say this was delta and delta prime, you can also show that this delta must be the same thing as delta prime. And so this is completely fixed by conformal symmetry. Now, of course, you could put an overall normalization, but then you could always just renormalize the operators to get rid of that overall normalization. So let's forget about the overall normalization. So it turns out that 2-point functions are completely fixed in terms of delta in conformal field theory. This is not the case in a regular quantum field theory. So this is already kind of showing the power of conformal symmetry. So if we now move on to 3-point functions, so now we can ask, okay, let's again look at scalars for simplicity. So we have 3 operators, so delta 1, delta 2, delta 3, at x1, x2, and x3. And so if we play a similar game, so this one is a little bit trickier to derive. This was done in Polyakov's famous paper with his collaborators, and they showed that this thing was fixed up to an overall constant, lambda, which depends on these 3 operators. So this is just some constant, but the position dependence is fixed to be x12 to the delta 1 plus delta 2 minus delta 3, x 23 to the delta 2 plus delta 3 minus delta 1, and finally x31 to the delta 3 plus delta 1 minus delta 2. So here the position dependence is completely fixed, just like it was for the 2-point function. But now there's a new quantity which is not fixed by symmetry, which is this lambda. And so this is another physical quantity, which is non-trivial, which kind of describes the theory. So in addition to knowing all the deltas and spins, you also need to know the lambdas if you want to completely understand the conformal field. Okay, and so now we could try to discuss the next higher point function, which is a 4-point function. So I want to kneel down, so let's write it here. So now let's ask how conformal symmetry constrains 4-point functions. And so kind of the fun ends here, in that it's not totally fixed. So if you now study a 4-point function, so this 4-point function is fixed by conformal symmetry, so there ends up being some overall factor. I'm assuming all the scaling dimensions are identical, just for simplicity. These are all scalars. So you take out this overall factor, but then the remaining thing can be any function of g and u and v. So just times this function. And so this function g of u and v is not constrained at all, where u and v are what are called conformal cross ratios. And so in particular, the values are, this is x12 squared, x34 squared, divided by x13 squared, x24 squared, and v is x23 squared, x14 squared, divided by x13 squared, x24 squared. Where this notation of like xij just means xi minus xj magnitude. Just make that clear. And so it turns out that, like, unlike the 2- and 3-point function, which were totally fixed up to maybe some constant, the 4-point function is only fixed up to an entire function of 2 different variables. So it's much less constrained. And so in subsequent lectures, we will discuss what you can say about higher point functions, but let's just stop at 4-point functions for now. And already, we discovered something kind of interesting, which is that here I said how to fix a 4-point function. And I said it depends on u and v. But this is Euclidean quantum field theory. In Euclidean quantum field theory, the ordering of these operators shouldn't matter. So you should be able to rearrange the order. And so in particular, if we swap, let's say, x1 with x2, using the definitions of u and v and this overall factor, this is going to have a constraint on g. So just rewriting this 4-point function with swapping 1 and 2, this is going to imply that g of u and v equals g of u over v and 1 over v. Okay, so this is one constraint. A second constraint, which you get from swapping x1 with x3. So again, just changing the definition of u and v in this overall factor, you're going to find that v to the delta times g of u and v equals u to the delta times g of v u. And so these two constraints, these are called crossing equations, which I'll write down because this is very important. And so these crossing equations, all they followed from was conformal symmetry and the fact that we're talking about a Euclidean quantum field theory such that the ordering of operators doesn't matter. Now, the ordering of operators also didn't matter for the 2-point function and the 3-point function, but in that case, you could just check that this position dependence was already trivially satisfying that property. So it wasn't telling you anything interesting. It's only for the 4-point function that this fact that you can permute the operators has a non-trivial implication, which is these constraints on this G. And so these constraints might seem very innocuous. You might be like, okay, whatever, this is some technical point, but it turns out that these constraints are the secret to solving conformal field. So what I said in the very beginning of the class of how you can estimate these numbers completely follow from this constraint. So this constraint is actually an extremely powerful constraint, and this is the origin of the conformal bootstrap, which is what we will explore in subsequent lectures. Great, so that concludes today's talk. So any questions?
Going back to the beginning of the lecture, can you please repeat 2 statements about the universalities you did? So you said that number of things we need to tune in the IR is equal to what?
So the number of relevant operators in the IR, which are singlets under the UV symmetry, is equivalent to the number of parameters you need to tune. So for instance, in the phi to the 4 theory, you had a Z2 symmetry. And it's going to be proven in subsequent lectures that there's just 2 relevant operators, basically phi and phi squared. And so this one is Z2 even, this one is Z2 off. Because just you're making phi go to minus phi, right?
Opposite, right?
Opposite, yeah.
Sorry. Great. So this one's Z2 odd, this one's Z2 even. And these are the only 2 relevant operators. And so because Z2 symmetry was symmetry in the UV, and because these are the only guys which are relevant in the IR, so IR relevant, thus you had to tune the one that's a singlet, the one that's invariant to the Z2, i.e. what you might call phi squared. And so that's why you had to tune one parameter in the phi to the 4 model in order to get the fixed point. And that parameter was g squared over m squared. So this is the only thing you had to tune for phi to the 4. In contrast, for the water vapor phase transition, here, even though in the IR there's a Z2, can solve the same CFT in the IR, in the UV, there is no symmetry because it's just random water molecules in a ball. There's no Z2. And so thus you have to tune all the relevant operators in the IR, which are invariant under the Z2, under the UV symmetry, which is nothing. So i.e. you have to tune both of them. And so you have to tune both relevant operators, and that's why there was 2 parameters you had to tune, pressure and temperature independently.
Is there a way to see which one of them is pressure and which one of them is temperature?
So I mean, that's a UV question. And so it would be some weird combination. So you could do it in practice, but that would just be
some combination of phi.
It would be some linear combination. So in particular, pressure and temperature would be related to this M and G. There would be some combinations. I should also note, as a technical comment, this is assuming that your UV preserves rotation symmetry. If your UV also breaks rotation, which I guess in principle could happen for some condensed matter system, then you would also have to consider operators that are relevant, which aren't scalars. So there could be spinning operators that are relevant. Although I think that's much more exotic. Any other questions? Also from people over the Zoom.
So I do have a question, so.
Yeah, sure.
Yeah, so if I was talking about a free system, then the 4 point would follow from products of the 2 points,
Yes.
right? So what do I have to do minimally to that thing you've written there so that I can just get that trivial limit?
Sorry, what would you have to do to see that these relations hold?
No, so how can I recover the non-interacting, like the free result where the 4 point correlation function?
What is G
becomes-
for the pre?
Sure. Okay, yeah, great. Yeah, so this will actually be in the exercises, but I can give a sneak peek. So in a free theory, so let's say it's 5 to the 4, where it's like or like I guess not 5 to the 4. It's just the free theory delta I squared. So in this case, the scaling dimensions, because it's a free theory, are the same scaling dimensions you had in the UV. And so recall that you could determine all these scaling dimensions just by the fact that demanding that this thing have dimension d. So that implies that phi has to have dimension d minus 2 over 2, and then every product of phi is to be d minus 2 over 2, times n. And so you just plug that delta into the 2-point function. So first of all, this tells you that a 2-point function of free operators would just be like x minus y to the 2, so say like O was both phi, so then you would have this thing, x minus y to the power d minus 2, which in particular if d is 3 would just be 1 over x minus y, which is the expected propagator, of a free scalar in 3 dimensions. And similarly, you would get the expected free answer for a 3-point function, just plugging in, the deltas for, free operators. And then similarly, so then for the 4-point function, you could just compute this thing using Wick contractions. And so you would get some answer, which would just be products of pairs of 2-point functions. And then you could verify that those products of pairs of 2-point functions satisfies these exact relations as expected. And so that's one of the exercises in the lecture notes. Yeah, so just a comment, I'm going to send an email to people in the class with a link to the lecture notes. And I encourage people to do them because, today's class was just kind of a very general introduction, a bit more theoretical. But in the subsequent lectures, we're going to be diving into the actual coding, and there's going to be example codes, etc. And so at that point, it becomes kind of super important to do the lectures because that's the only way you'll be able to follow all the coding details. Any other questions? I saw there were some comments on the thing. I don't know.
Oh, I was asking about whether they hear or not.
Oh, you were just asking. Okay. So any other questions about?
So is there some nice relations about for the non-relativistic, like the field theory, with the scale invariance as well?
Oh, you're saying relevant to the theories that she was asking about before, like the
non-relativistic.
Well, okay. So
Yeah.
one interesting fact about non-relativistic systems is that many non-relativistic systems, when they undergo a second order phase transition, they have emergent relativistic symmetry. And so that's why conformal field theory is relevant to condensed matter. So even though in the real world, not real world, but even though in everyday energy scales we don't see relativity, you could have some magnet which you don't see relativity. Nonetheless, when you tune it to second order phase transition, it's described by the Ising model.
But some will remain to be non-relativistic, right? But they still have a scale invariance. Then do they have some nice features?
So yeah, okay. So there's something called the Schrodinger group, which is a subset of the conformal group where you break relativistic invariance, but you still have scale invariance. And so that does imply some constraints, but the constraints are not as powerful. And so that does exist and people have studied it. But the conformal bootstrap doesn't work in the case of Schrodinger symmetry. As far as I know. It's you really do need the emergent relativistic.
So you mean they are not enough constrained?
Yeah, they're not sufficiently constrained.
I see.
Because in that case you might have scale invariance, but now you've broken the Poincare invariance to some subgroup.
I see.
But thankfully in most everyday systems, I don't know most, but in many everyday systems, the second order phase transition is a CFT with all the relativistic symmetry.
Sorry, just to clarify, it's not really relativistic, right? It's just Euclidean conformal group, so it's not really relative.
Okay, because it's Euclidean, you can say maybe you object to the word relativist.
Yeah.
But the thing is that you could also have the Lorentzian conformal group and it would have the exact same constraints.
That's true, but in the case of Ising model, magnetic systems, it's not a relativistic symmetry that is emergent. It's just a Euclidean,
Yeah, but
rotational symmetry.
that's not even necessarily true because so I discussed before how CFTs occur in two different kinds of systems, like statistical systems and quantum phase transitions. And so quantum phase transitions really do have the Lorentzian conformal group. And this is even though they are condensed matter systems, which in the UV didn't have relativity. So like a superfluid or something is really described by the Lorentzian O2 model.
That's right.
Now, it just turns out though, and there's also this kind of like fact you might know from statistical physics, which is that if you have some like classical theory in like d dimensions, it's the same thing as a quantum theory in d plus 1 dimensions. And so that's kind of like it's kind of like the same idea. So like conformal field theory, the constraints discussed in this lecture and in the subsequent lectures apply identically to Lorentzian CFTs versus Euclidean CFTs. So like the differences between Lorentzian and Euclidean are outside the confines of this class, I won't be discussing. In both cases, you can apply bootstrap.
Consider, say, a sphere as that is the space of conformal transformation of the sphere. Do I get also?
Well, a sphere is conformally flat. So if you could also discuss manifolds that are not conformally flat, and then you would get constraints. And that's an interesting subject for research, like defects. So any further questions? Okay, otherwise, I guess we're done for today, and I guess I'll see you guys on Wednesday, hopefully. Out of curiosity, so okay, there was people from Columbia who came, and there's people from NYU, obviously. Did anybody come from other places? What's that? Flatiron. So you guys came from Flatiron? Yeah.
No.
Sorry. And CUNY. Oh, great. Okay, so we actually did get people from every place.
Okay,
That was my hope. We would have some representatives. And this